Welcome to another fun-filled ride through the Northwest Mark 2023. Here we go with episode 6.
So welcome to episode 6. Pause the video here, check out the problem, and try to see if you can do it. Let's go. So state the assumptions of the kinetic theory of an ideal gas. Okay, so the assumptions, easy peasy. Collisions between molecules on the walls of their container are elastic. Okay. Next assumption, volume of a gas molecule is negligible compared to volume of the gas. Third assumption, time spent during collision is negligible compared to time between collisions. Fourth assumption, the intermolecular forces between gas molecules are negligible. These are the four major assumptions for the ideal gas equation. Any other thing really is not measure, really. Uh, so we want to use the assumptions to derive an expression for the pressure P exerted by an ideal gas of density rho on the walls of its container if the mean square speed of the molecule is. Okay, so this is our container right here. This is a molecule. It has components of velocity in the y, x, and z direction. Okay, so let's do some work. When a molecule hits A, B, C, D, so it gets all the way and then it hits this side A, B, C, D, you realize that there's a change in momentum, right? And what's the change in momentum? Initial momentum, which is mu, minus final momentum, which is negative mu because it reverses the direction. So you have 2 mu there. So our force is, according to Newton's second law, time rate of change of momentum, okay? So 2 mu divided by time. And what is the time? Hey, remember that you're traveling from here to here. All right, you're using and back. So for me to move from this wall, get over here, hit this wall, and then get back here, I need the dimensions of this wall. Okay, so the dimensions of this cube here is basically L by L by L by L units. So if I'm traveling from this face down to this face and then back to this face, what's the time I'll take? I'll take this distance, or the time is the total distance covered divided by the velocity, and the total distance covered is L plus L, all right, because you hit and then you come all the way and then back there, so that's 2L, right? And then divided by the velocity in this direction, which is just U. So that's it right there. That's why I put the time like that. So our force now is 2mu squared over 2L when you simplify this expression now. So our F is mu squared over L. Now, but notice that pressure is force over area. And so our pressure by one molecule of gas is basically what? Our force is mu squared over L. Our area is L squared. Remember that the area here will be L times L, which is L squared. So you have mu squared over L cubed there. Now one can get the pressure exerted by all the molecules of gas that are available in this container. And if there are n molecules of gas, okay, so they are going to exert a total pressure of n times the pressure one would exert, which is simply mu squared over L cubed. Okay, so you multiply that by n. Now this L cube, remember that is the volume of the container, so that's why you just see me putting V there. So, but notice that, hey, the mean square speed in this system, right? Because this gas molecule has three components of speed, in the y, in the x, and the z direction. So what's the average speed? The average speed is c, okay? And now what you need to know is that the mean square speed in any one of these directions is equal to the other, all right? Because the intermolecular forces are negligible, so their mean square speed in every one of these directions will be equal. That's what makes the motion of gas molecules random, okay? They can move in any direction, right? So you realize that, hey, u bar squared equals v bar squared equals w bar squared. And so you notice that, hey, since my mean square speed would be d squared plus d squared plus d squared. So you're getting the velocities in each one of those directions and then you're squaring, all right? Of course, the mean velocity in each one of those directions. So you notice that our mean square speed would basically be what? 3 mean square speed in any one of the directions. Why? Because they are all equal, all right? The mean square speed in y is equal to x, is that in x is equal to that in z. And so the mean square speed will just be 3 times the mean square speed in any one of those directions, okay? So you realize that our mean square speed in the direction y there would simply be 1/3 the total mean square speed of any gas molecules, right? Gas molecule right there. And so you realize that, hey, our pressure then becomes what? 1/3 nm instead of u squared here. What will I put? Remember that my u bar squared is what? Is 1/3 c bar squared right there, right? So you get 1/3 there, C bar squared, and then of course, but Nm over V is density. What is Nm? M here is the mass of one molecule. N is the total number of molecules. So N times M gives me the total mass of the gas divided by the total volume of the gas. That gives me the density of the gas. So you notice that my pressure here is 1/3 rho C bar squared. Okay, and so the B part says 8 gas molecules have the following speeds, all of these speeds. Calculate the mean square speed and the root mean square speed of the molecules. So the mean square speed would basically get in the square of every one of these speeds divided by the total number of molecules. So 20 squared, that how many molecules are there? There are 8 molecules. So that's how you get the mean square speed. Remember that it's meter squared per second squared. It's mean square speed. And then the next thing you can get is the root mean square speed, which is basically finding the square root of this thing now. So the square root, the root mean square speed there is 59 meters per second. Good. So let's move over to the C part. The C part says state Kirchhoff's circuit laws. Well, that's easy, right? Law 1 is algebraic sum of all the currents entering the node is 0. Law 2 is algebraic sum of all the EMFs in a closed loop path is equal to the algebraic sum of all the potential difference dropped. Okay. Good. And so we can talk about calculate the potential difference across the 4 ohm resistor in figure 1. This is our figure, but I've already indicated the loops and then the direction of our traverse already, right? And so you realize that, hey, from our Kirchhoff's current law, I is equals to I1 plus I2. Okay, this is our I here, split into I1 and I2. And then our I, of course, the so -1 equals I2 minus 4 I1. Okay, so boom, you get this guy as this, so you can rearrange the equation, right? Good. So we can go ahead and say, all right, so sorry, this is, oh Jesus, sorry, I've messed this up a little bit. So this is Kirchhoff's current law, right? And then this is from Kirchhoff's voltage law. So I'm applying this from loop 1 here. So I've applied that in loop 1 here. No, loop 2. This one is coming from loop 2, right? This one from loop 1. Yeah, from loop 1. Sorry, really sorry, guys. So some of EMFs, if I traverse like this, remember that this I'll be moving from positive to negative. So this EMF source will be negative. So I have -1 there. And then this PD source here would be, so I have, there's a resistor here which is 1 ohm. So the current through it is I2. So I'll just have I2 times 1, which is just I2. Then when I traverse all the way back like this, I'll be traversing against the direction of flow of current here. So this PD here will be negative. So I have -4 I1. Right? So I can rearrange that and I get equation 2. And then I get down here and I apply loop laws to loop 2. Okay. So if I traverse like this, I have 2 volts because I'm traversing the direction of the EMF. So 2 volts equals the current that goes through this guy is I, and the resistance here is 0.5. So I'm traversing the direction of the current, so that makes 0.5 I here, plus 4 I1 because I'm traversing the direction of this guy too. So I can rearrange and then get this. If we can simplify, really, you just solve, just really solve, and then you get that I1 is 0.23 amperes. So if I1 is 0.323 amperes, so our V across the 4 ohm resistor basically what I1 times R, right? Which is 0.23 times 4, which is 0.92 volts.